Let us solve a question on utility maximization using Lagrange's method. The question is, find the optimum commodity purchases for a consumer whose utility function is, utility is a function of two goods Q1 and Q2, which is equal to e raised power Q1 times Q2. Prices of Q1 and Q2 are being given as $1 and $5 respectively, and the income of the consumer is $10. Okay, so how do we solve it using Lagrange's function? Let us find out. So we are being given the utility function. Okay, since we want to maximize utility here, so we have to maximize, and let's write here, maximize the given utility function u is equal to e raised power Q1 times Q2. Okay, this is our utility function, and we have the budget constraint for the consumer also. What is the budget constraint? And let's write it here. So that is P1, that is price of Q1 times units of Q1 plus price of Q2 times units of Q2 should be equal to income of the consumer. M denotes the income here. Okay, so what the consumer wants to do, he wants to maximize this utility function subject to the budget constraint. P1 is $1, P2 is $5. So I can write it as Q1 plus 5 Q2 should be equal to, and what is the income of the consumer? $10. Okay, to solve it with the Lagrange's method, what we need to do, first we need to find out the Lagrange's function here. Okay, to find out the Lagrange's function, first we need to solve this budget constraint. We equate it with 0, and in place of m, as I have told you, it is equal to 10. Okay, let us set it equal to 0. That means 10, transposing these items, we will get minus Q1 minus 5 Q2 is equal to 0. Okay, first step is to set it equal to 0. Then the next step is to multiply this resulting constraint by lambda. Let us multiply it by lambda. Then we are in a position to form the Lagrange's function, and Lagrange's function is actually equal to the given utility function, which is e raised power Q1 times Q2, and to this utility function, or we also call it the objective function, we add this resulting constraint, that is we write plus, then we write this resulting constraint, that is lambda, times this 10 minus Q1 minus 5 Q2. Okay, this is our Lagrange's function. Now to find out the optimum values of Q1 and Q2, what we need to do, we partially differentiate this Lagrange's function with respect to Q1, Q2 and lambda, and set it equal to 0 simultaneously to find out the optimal values. Okay, so for that, what will we do? We partially differentiate L first with respect to Q1. Let us denote it by L1, that is, or let us suppose L1 denotes the partial derivative of this function with respect to Q1. Okay, what is the derivative of this function e raised power Q1 times Q2 with respect to Q1? So it is simply e raised power Q1 times Q2 times the derivative of this coefficient, which is in this exponential function here, that is the derivative of Q1 will be 1, so we are left with Q2. Okay, let me explain it here. If we have e raised power nx, its derivative is simply the given e raised power nx first times the derivative of the exponent with respect to x. So derivative of x is 1 in the x here, so we are left with n. Okay, we are using the chain rule here. So the derivative of e raised power nx is equal to e raised power nx times the derivative of the exponent with respect to x. Derivative of x will be here 1, so we are left with n. So if we have e raised power 5x, let us suppose, its derivative is simply e raised power 5x times the derivative of 5x here. Okay, so which becomes e raised power 5x times derivative of x will be 1, so we are left with 5. Same we are doing here. So derivative of this stuff with respect to q1 will be equal to this e raised power q1 times q2 times the derivative of exponent. The exponent is either q1 times q2, so derivative of q1 is 1, so we are left with q2. Okay, so this was necessary to make it understandable to you. Then we need to, since we are taking the partials with respect to q1 here, in this equation, rather in these terms, only q1 is in the middle term, so derivative of q1 is here -1, so we have -1 times lambda is minus lambda, and we set it equal to 0. Okay, similarly L2 denotes the derivative of this Lagrange function with respect to q2, and here by the same logic, what will we get? So we have e raised power q1 times q2 times the derivative of the exponent with respect to q2, so derivative of q2 will be 1, so we are left with q1. Here the derivative of q2 is 1, so we are left with -5 into lambda, that is 5 lambda, and we set it equal to 0. Then we take the partials with respect to lambda, so derivative of lambda is 1 here. No lambda is involved in the first term, its derivative is 0. Derivative of lambda is 1, so we are left with 10 minus q1 minus 5 q2 is equal to 0. Okay, after that what will we do? Let us rewrite this function first. Okay, I can write it in this fashion: e raised power q1 times q2 times q2 is equal to, transposing this lambda, it will become plus lambda. In the same manner, this L2 denotes implies e raised power q1 times q2 into q1, transposing this -5 lambda to RHS, it will become plus 5 lambda. Okay, let us suppose this is equation first, this is equation second, let us say this is equation third here. Okay, what will we do next? We divide equation 1 and equation 2. Okay, let's write it here. Equation 1 upon equation 2 implies, which implies, let's write it here. So we have e raised power q1 times q2, then we have q2 here. To this we divide by this e raised power q1 times q2 times this q1 is equal to lambda upon 5 lambda. Okay, here lambda gets cancelled, this e raised power gets cancelled, we are left with q1 upon q2 is equal to 1 upon 5. Okay, solving for q1 here, which implies q1 will be equal to 1 upon 5 q2. Okay, next we need to plug the value of q1 is equal to this stuff into the third equation. Okay, in this equation, when we put the value of q1, what will we get? We have 10 minus q1 is this 1 upon 5 q2 minus 5 q2 is equal to 0, which implies 10 will be equal to, transposing these items, it will become q2 upon 5 plus 5 q2. Okay, which implies 10 will be equal to 5 5s are 25. Okay, we will get here 5 5s are 25 q2 plus q2 is 26 q2 upon 5, which implies q2 will be equal to 10 into, transposing this, it will become 5 upon 26. Let me see if I have done any mistake. Okay, I have done a big mistake in calculating the values here. Okay, and the mistake is here. We have q2 upon q1, I have written q1 upon q2. Okay, so sorry for this. So we have here actually q2 upon q1. Okay, so q2 upon q1 is equal to 1 upon 5, which implies, again I have done mistake, so q2 is equal to actually 1 upon 5 q1. Okay, I was wondering why I got this result. So plugging the value of Q2 is equal to this stuff into this equation. So we have 10 minus Q1 minus 5. In place of Q2 we have this 1 upon 5. 1 upon 5 Q1 is equal to 0. 5 and 5 gets cancelled. We are left with 10 minus Q1 minus Q2 is equal to 0, which implies 10 is equal to Q. Okay, so here we have again Q1 and Q1. So Q1 plus Q1, okay, which implies twice Q1 is equal to 10, implies dividing both sides by Q1 we will get Q1 is equal to 10 upon 2 is 5. So optimal level of Q1 will be equal to 5. And what about Q2? Simply plug Q1 is equal to 5 in this equation to find out the value of Q2. So Q2 will be equal to 1 upon 5 into the value of Q1 is 5. So we will get the value of Q2 is equal to 1. Okay, that implies Q1 Q2 optimal bundle that the consumer should buy to maximize utility will be equal to he will consume 5 units of good 1 and 1 unit of good 2 to maximize utility. Okay, and we can also find out what we call the total utility derived. So what will be then total utility derived, which will be equal to, we simply plug the value of Q1 and Q2 into the utility function to find out the maximum utility, which is equal to e raised power 5 into 1. So which is equal to e raised power 5. Okay, and we can then solve this for, we know E is equal to 2.71 something raised power 5. Okay, I don't know the exact value here. So solving this we will get the utility derived by the consumer. I hope I make myself clear in this video. Thank you.